Hello, ladies and gentlemen, and welcome back. Today we're going to be talking about some properties of exponents. Now, I know what you're thinking. Mr. O'Neill, aren't we supposed to be like having a number involved here, like lesson 7-4 or 7-5, or maybe even 7-6? Well, yeah, we are. Supposedly. My chair is really creaky. I need to get a better one. Maybe, hopefully, that will happen in the near future. Hopefully. Anyway, properties of exponents. My issue with the way this book has been doing properties of exponents is that it doesn't actually talk about all the different properties of them until 7-5. And in 7-5, it talks about the rational exponents and radicals. After it talks about the multiplication and division properties of exponents. So you know what? We could call this 7-5, but then you get a little bit scared because what about 7-4? So we're going to do 7-4 really hard, really fast, really easy. But you said really hard. We'll go hard at it? No? That doesn't work? Oh well. Anyway, it's 10:21. I've been up for more hours than I want to count. And I'm still having to teach. So please give me a break, okay? And not of a Kit Kat bar, because I've had too many Kit Kats today. Kit Kat. Anyway, let's look at some of the properties of exponents. So far, when we've looked at exponents, when we see something like a to the b power, we call this bottom portion the base, and this top portion the power. And the power tells us how many times the base multiplies by itself. So for an example, if I saw 4 to the third power, we know that's 4 times 4 times 4. And if you get 4 to the seventh power, you get 444, and then 44, and then 44. Actually, 4444, which is actually a phone number for pizza in the Austin area. So if you're in the Austin area and you want some pizza, here's a phone number. But we're not in Austin. We're in this place called Ketchikan. Beautiful place with lots of rain. Yeah, that'll make the people from Austin jealous. We have rain. You might have pizza, but we have rain. You might have movie theaters, but we have rain. You might have more than 4 fast food restaurants, but we have rain. No, to be honest, I love it here in Ketchikan. I wouldn't want to live anywhere else. So what would happen if we had, let's see, 4 to the second power times 4 to the third power? Now, I know we've gone over this before, but basically the idea was we break it down into its original format, and then we kind of come up with an idea that says, hey, isn't that the same as this other thing? And then we say, well, yes, it is, by definition. And so we start using that other thing. In other words, if we have two things of the same base, we add the exponents. Sorry, two things of the same base multiplied together, we add the exponents. So, with that in mind, we're going to do some experiments and some thoughts about how things work together and come up with the remaining properties of exponents. Okay, so when multiplying things of the same base, we added them. So what would happen if we divide things with the same base? Well, that's the same thing as, let's see, 4 times 4. 4 to the fifth over 4 to the third is what we're looking at. We've got 1, 2, 3, 4, 5 fours there. And then underneath we have 1, 2, 3 fours. And if you remember from when we were learning how to reduce, if the same number appears both in the numerator and the denominator, and there's no addition present, it can cancel them out. So I can cancel those 4's out, and I can cancel those 4's out, and I can cancel those 4's out. And what am I left with? Well, I'm left with 4 times 4, which is 4 to the second power, which is 4 to the 5 minus 3. What's 5 minus 3 again? Yeah. So when we're dividing things with the same base, what do? The exponents? We subtract. When multiplying, we add. When dividing, we subtract. Seems easy enough. Excuse me. And then we're thinking about roots, right? So if I had something like 4 to the 4th power, that's like saying 4 squared. Oh, wait, well, we haven't got to that point yet. Well, let's see what happens. Let's do that part first, actually. What happens if we raise a power to a power? In other words, say we have 4 to the 2nd power raised to the 3rd power. Well, by definition, this is 4 squared times 4 squared times 4 squared, which is 4 to the 2 plus 2 plus 2. Isn't adding the same thing over and over again the same thing as multiplying? And the answer is yes. So isn't that the same thing as just multiplying them? And the answer is yes. So this is really 4 to the 2 times 3, which is the same thing as 4 to the 6th. Which led us to the next idea. The next idea is what happens if I want to undo a power? Because going one way is great, but being able to go both ways is what math is all about. So let's say for a moment that we had 4 to the 6th power. And we wanted to take that guy and find out. Actually, let's look at a different one. Let's look at the square root of 16, which is basically saying what times itself gives me 16. Well, we know 16 is really 4 to the 2nd power in disguise, right? So when we're looking at the square root, we're saying what number times itself gives us that number. So if we're looking at the square root of 4 squared, that means that our x would be equal to 4. So how do you turn 2 into 1? And the answer is fractions. So if I'm looking at a fraction root, say 16 to the 1/2 power, what I'm really asking is what times itself gives me 16. So if I'm asking what times itself gives me 16, I would say that would be either 4 or negative 4, but we're just going to use the positives now. So that would be 4. Which leads us to the next idea, which was this entire lesson, or actually lesson 5, 7-5, which is if you have an index on the inside of this radicand, right? This weird hook-shaped thing that looks like this, and then usually there's a number on the inside. If you have an index number on the inside there that says how many times a number multiplied by itself gives me the number on the inside, we can convert that into x to the 1 over m power. So if I saw something like x to the 5th, and then I was taking the 3rd root of it, we could change this into x to the 5 over 3. Now, putting it all together, putting all of our ideas together, how is this useful? How is this useful? Well, It's useful when we're trying to solve complex exponential problems. So we're just going to go ahead and skip 7.4 because, believe it or not, we already know it. We've already gone over it. We know about the negative exponents mean that we go up or down. So what we're going to look at is some more complex ideas. So for an example, what if I have a to the 2/3 times a to the 1/4? Well, since we're multiplying, we add the exponents. So shouldn't this be the same thing as a to the 2/3 plus 1/4? And we know how to add fractions. 4 times 2 is 8. 3 times 1 is 3. 3 times 4 is 12. 8 plus 3 is 11. So this becomes a to the 11 over 12. So all those practice problems involving fractions have shown up again. Who'd have thought? And then if we had some fun ones, right? Let's say for a moment that I have 16x to the 4th power, and I'm finding the square root of that whole thing. Well, fortunately for us, we can kind of separate them into two separate things because it's by multiplication. So what I'm really looking at is what is the square root of 16 and what is square root of x to the 4th? Well, we know the square root of 16. That's 4. But this x to the 4th thing is a little more complicated. So let's look at it again. If we remember, the nth root becomes the denominator for a fraction. So really this is x to the 4th power and then divided by 2, or 4 halves. If you want to see that in more slow motion, because I'm skipping steps because I'm way too tired, this is the same thing as x to the 4th times, because it's a square root, 1/2. And when you raise a power to a power, you multiply the exponents. So that ends up being x is equal to 4. Let's see, 4 times 1/2 is 2. 4x squared. But wait, there's more. What if we're looking at the cubed root of 8b to the 5th minus the 4th root of 256 a to the 3rd? What can we do with these two guys? Some of you are saying, Mr. Neal, they have different variables, so we're not going to be able to combine them. And I'm like, you're right, but we can still simplify them a bit. We can still get them out of their little boxes, out of their houses, into the woods, and enjoying the beautiful weather of Ketchikan while they get drenched in rain. So the cubed root of 8 is what number times itself? 3 times gives you 8, and that's easy. That's 2. 2 times 2 is 4. 4 times 2 is 8. And then b would go to the 5 over 3 power. So b to the 5 over 3. Now, 256, 1/4. Let's see, I think that's 4. Let's see, 4 times 4 is 16. And then 16 times 16. Let's see if that does it. 6 times 6 is 36. So that'd be 9. And then that would be 6. And that'd be 1. And that'd be 6. And that'd be 5. Oh, look at that. So the 4th root of 256 would be 4. and then the a would go to the 3/4 power. Now, could I do anything else with these numbers? The answer is no. They're not like terms, so we can't combine them in any way. Even if they were, it's subtraction. Can't really do anything with subtraction. If you remember that tier system that I taught you guys in the beginning, you have addition, and then addition over and over again is multiplication, and multiplication over and over again are exponents or powers. How we'd always go down one, right? Like a power to a power becomes multiplication, and then multiplying things of the same base, you add the exponents. But if you're adding two things of the same base, you don't do anything to the exponents because there's nothing there. Clearly, there's nothing here. So if you remember that tier system on how to remember what you're supposed to do with which exponent level, you would recognize that even if they were the same base, even if they were both b's for the base, we wouldn't be able to do anything at this point because the powers are different. So that's as far as we could go. Anyway, I think the best way to learn is through experience, and I think you guys could use some more experience on this stuff. So, it being 10:30 and I having been up for way too many hours, I think it's time that you did some practice on your own. So your practice should be the following. And the concepts are basic, but the things that you can do with them are so infinite. So I'm going to give you some problems, and it's going to be from both 7-5 and 7-4. So for 7-4, we're going to do some easy ones. Mr. Neal, this is too much homework. Well, this video is like 15 minutes long, so you should have plenty of time. Plenty of time to do this stuff. And this stuff is actually super easy. So like when I say that you can do 8 through 23 evens, you'd be like, that's 10 questions, so that should be super fast and easy. And then when I say, okay, now we're going to do 7-5, and again, these ideas are super easy. Actually, I'm going to give some more from 7-4. Ha ha ha. Fooled you. 33 through 48 evens as well. And then on the other side of things, yes, this does mean that they're all super easy. Yes, miss, yes, they are super easy. And then we're looking at 7-5. And 7-5 has some funsies that you guys are going to enjoy. So I'm going to let you enjoy figuring out numbers 11 through 34 evens. So really it should be like 12 through 34, but I'm too lazy to write 12. And then for the really fun ones, 43 through 48. And since that's only 6 problems, you can just do all 6 of them. And that should give you the practice that you need for dealing with our next idea, which is going to be graphing exponents. So yeah, if you don't remember how to graph, now would be a great time to brush up on that while you finish up with your exponent homework. And as I'm very fond of saying, good luck, have fun, smile and be happy, and I will see you guys tomorrow. Bye-bye.